so before we get into material, I just wanted to kind of give a heads up as to where we are since it's been a little while since we've had a live lecture. Um, for so for this week, for Monday, you should have watched the two videos on improper integrals. And it's divided into two videos, but they're both relatively short. So I think under 45 minutes total. But so there are two videos on those, and then there's a worksheet for practice uh, with answers, but not like worked out solutions that I put, and that is in the Unit 1 folder because that material technically is not sequence series. So it's in the Unit 1 folder, and then it's folder 8. So this worksheet is in Unit 1, folder 8. I'm not going to collect that. Whoops, folder. I'm not going to collect that, but that is where you should practice improper integrals. So you have, I think there's 10 practice problems and then the 10 answers to those. And then next week when we're doing review sessions, if you want to work out any of those together, we certainly can. But I did a bunch of examples on those videos too. So that's what you should do for Monday if you haven't already. No real deadline on that. You have a test next week. So just make sure you get it done before then. But I'm not collecting any of that. Yesterday, obviously, we did not have class because of election day. And then so today, we're going to be talking about the integral test. And we won't talk too much about it. We'll talk about the idea and do a couple examples. But that's the topic of today's lecture. And then there's a worksheet on that too. So, and then you have worked out solutions that you definitely should go through before the test next week. But this is in Unit 3, folder 2, I believe. Let me double check that. But I think it's Unit 3, folder 2. And yeah, so Unit 3, folder 2, and it's file number 5 and 6. Folder 2, and then it's files 5 and 6. 6 is the solutions, 5 is the actual handout. So you should work through that. It actually takes you through how to derive p-series, and we'll talk a little bit more about that toward the end of the lecture, but that's kind of the big result from integral test that we use in this class. So we'll talk about that when we get to it. And then just kind of give you a heads up as to what's coming up. Tomorrow's lecture, we will cover the ratio and the root tests, and not that the other topics are not important. They are, but these are bigger topics for next week's exam. So ratio and root tests will be tomorrow. And then series 4, which you've already worked on, numbers 11 through 19, those are going to be due on CrowdMark next Monday. You again have solutions. So like when you're submitting problems where I'm giving you the solutions, I definitely want you to do your own, but you can use my solutions. Just make sure you genuinely understand them because we're just grading that you did it. You get credit for having done that, but do make sure you understand it because you got to be able to do the same types of stuff on next week's exam. So that takes us through the end of this week. There won't be anything for Friday. This is the only assignment of that that's going to be collected. So you will not hand in the other stuff. You should do it and make sure you're comfortable for the test next week. But only series 4 for this week is what is due next Monday. So that's kind of the schedule. The test will cut off there. So exam 3 is next Thursday. And it will stop with the ratio and root test. So it will cover all material through tomorrow. I need to work on the schedule for the rest of the semester as far as what next week will look like. There's a possibility we'll have a lecture on Monday or Tuesday that will be new, that won't be on the exam. There's also a possibility that we won't do that live, and live will be a question and answer session for that. So let me work on that and figure out what I think is probably best for everybody, because I want to make sure we're ready for the exam next Thursday. But there's a good possibility we'll have to start into new material next week, whether that's live or pre-recorded lectures. Okay, so there's a question in chat, but if there are any questions about this, this is a good time to ask. I did not mean for it that you can only text me privately. You can text everybody. But somebody in chat asked, will there be a written section? That's still unclear, and I will let you know as soon as I'm aware of that. But chances are I won't know that until at least Monday. All right, sorry, I'm not trying to hide that from anyone. I just have to mess with WebAssign more before we know whether that's going to be possible, whether that's going to be needed. Sorry. Other questions?
Yeah, I have a question for the series 4. Should we wait till after the Thursday lecture to try to do it, or can we do it? Okay.
Well, I mean, it's nothing that you would have learned from me through today.
Gotcha.
Yeah. So like, if some people are taking this again or have, seen sequence series before, that's different, but we have not talked about any of it in this class. Okay. I'm not saying that's you. I'm just saying in general. All right. Other questions? Other questions, you guys? All right. So that's kind of what's coming up. And I will keep you posted on the exam as soon as I know. I would definitely look at old exam 3 and 4. So you have a whole folder of old exams online, or on the shared drive. So make sure you go in there. You have worked out solutions to those exams. If you see stuff about power series, that's something we haven't talked about in here. So like, if you see some questions, especially on series 4 or on exam 4, sometimes we get further on exam. In some semesters we have 4 exams. We only have 3 this semester. But when they're 4 exams, sometimes the 4th exam covers more than what will be on this exam. So, you can read, and if it looks like we've never done it, obviously, then we have not. But any problem that says show whether the series converges or diverges, that is part of what we've done. Same with sequences, obviously. So that is part of what's on this. If we're starting to talk about interval and radius of convergence, which we'll talk about later, that is not something that would be on this exam. All right, any other questions before we kind of get into the integral test part of this? Okay. All right, so if you do have any questions, just let me know. And then actually before the end, I may get kind of a feel of how many people, how we want to structure next week, because I'm kind of open to ideas for how that is best for you guys. But okay, let's talk about the integral test. So the idea of the integral test is you have a series, AK, and that normally would start from 1 to infinity, but it technically doesn't have to start at 1. It doesn't matter a whole lot where it starts for this idea. But it's a series where the terms in this series are positive. Okay, so the terms of the thing that you're adding are positive. And we're going to have that they are decreasing and they approach 0. So we'll talk more about that in a minute. But actually, let's go ahead and start stating the integral test, and then we'll get a conclusion kind of together. So, okay, what the integral test says is that suppose f of x, or f of k, is equal to ak for k greater than or equal to 1. Then if f of x is continuous, positive, and decreasing, then we can make a conclusion. And so I want to talk about what that looks like. So in practice, what's going to happen is we have this sequence AK, and we'll put that in blue. So you have the sequence AK where the terms are all positive and they're decreasing to 0. Okay, if they weren't going to 0, so if AK were not approaching 0, why would we not really need to talk about the series? If this limit of the blue dots was not 0, what would happen to the series? What do we know about that? You guys remember? So if the limit of the sequence is not 0, what does the series do?
It would diverge.
Yeah, it diverges. So we're going to assume that it is 0. That means it's possible that it converges. And so when you have this condition, f of k equals ak for k greater than or equal to 1, then what happens is you have this function f of x where the blue dots are along that function. And so we'll make these blue dots a little bit bigger, but these dots are along the function. And so these conditions, that f of k equals ak just means the dots are along that continuous function. F of x is continuous, positive, and decreasing means that it looks like that. So it's continuous. So, it's this nice smooth curve. It's positive, meaning it's above the x-axis, and it's decreasing, meaning it's always going down. That means the graph basically looks like that. And so it doesn't, based on what we've said here, it doesn't have to go to 0. But if it doesn't, then we know the series diverges anyway. So we're only worried about if the picture looks this way. So there's several things here that are true. There's one that f of k equals ak, meaning the dots lie along that curve. F of x is continuous, positive, and decreasing, mean basically it looks like this. And so, okay, if we have this picture, is basically what we're saying there. And so I'm actually going to draw it twice. And this is supposed to represent the same one. But on a screen, it may not look exactly the same. But you have this sequence AK along this continuous positive decreasing curve, and it decreases towards 0. So I'm going to put 2 pictures on the board or on the screen. So one is I'm going to look at this and say, okay, well, this is A1. This is A2, this is A3, A4, and A5. And if I draw in this rectangle, so I draw in all these rectangles, almost like a left-hand sum. So if I draw these, what is the area of that rectangle? So the base, if this is, in my bad, I labeled this maybe poorly. So A1, I mean, is the Y value up there. This is technically, I guess, 1, 2, 3. I don't just guess, this is correct. So A1 is the Y value. This is 1, 2, 3, 4, 5. So if A1 is the Y value, and this goes from 0 to 1, what's the area of that rectangle? What do you guys think?
It's just A1 times 1.
Yeah, it's A1 times 1, so it's just 1. And then the area of this rectangle is A2, and the area of this rectangle is A3, and so on. Does everybody see that? Everybody good? Okay, and so this is a convincing picture that this inequality is true. And let me know why we think this is a true inequality. So not from 1 to infinity, but the sum from 2 to infinity. So A2 is this area, A3 is this area, A4 is this area, A5 is this area, and so on. That sum is then less than or equal to the integral from 1 to infinity of f of x dx. Why is this picture a pretty convincing argument that this inequality is true? What do you guys think? Again, remember it's going from 2 to infinity. So why do we think this is showing that this is the case? So what is this series represented by? The series from 2 to infinity, what's that represented by on this diagram?
Is it like the area starting from box 2?
Yeah, it's the area starting from the second box, the second rectangle. So this one's A2, this one's A3, this one's A4, 4, A5, and so on. And so that area, how do I know that's less than this integral from 1 to infinity? What's the integral from 1 to infinity going to represent?
The area under that curve from 1 to infinity.
Yeah, the area under that curve from 1 to infinity. So the fact that you have a gap above every one of those rectangles means this is true. Now, A1 isn't included here, but this inequality is true. Does everybody see that based on what we're saying? Okay, now, if I draw the picture differently, I could draw what's similar to a right-hand sum. And now the area of this rectangle is A1. This rectangle is A2. This one's A3. This one's A4. A5 would be over here. And so this is a pretty convincing argument that this is the case. And so, okay, how come it's possible that both of these inequalities are true? So I'm saying less than here, greater than here. What's the difference? What do you guys think?
Where you start.
Yeah, where you start. So this one starts at 1. And so now when I throw it to the right, now you've got this extra area above the curve every time. So if we include this one and we put it this way, well, okay, A1 is over here. A2 is this area. A3 is this area. Well, now that sum is bigger than this infinite integral or this improper integral. Does everybody see that? Everybody clear? Okay, so last week when we were, or maybe even the week before, when we were talking about comparison tests, we said that when you have this condition, that all the terms are positive, there's only one way for the infinite series to diverge. What is that? So if all the terms are positive, then how is it that a series can diverge? What's the only way for that to happen? What does it do if it diverges? And they're all positive. If everything you're adding is positive, how do you get a series to diverge? If it goes to what? No one remembers? Okay, so in general, how can series diverge? They can go to infinity, they can go to negative infinity, and they can bounce between several values or a couple values. So if you're adding all positive numbers, could you go to infinity? Yes.
Yes.
Could it go to negative infinity?
No.
No. And then could it bounce between two values if you're adding all positive numbers?
No.
No. And so the only way for this to diverge, if all the terms are positive, is if it goes to infinity. So, okay, so let's say, so improper integrals was the topic of the video you guys watched on Monday. Those either converge or diverge as well. So same argument works. If these conditions are satisfied, then if this integral diverges, then it goes to infinity. So if I know that the integral from 1 to infinity of f of x, if I know that it diverges based on these two pictures, what would I then know about the infinite series or an infinite series? If this diverges, that means this goes to infinity. So then which inequality is helpful? What do you guys think? So if the integral goes to infinity, it diverges, so it goes to infinity, then is it helpful to know that the series is smaller than infinity or to know that the series is bigger than infinity?
Bigger.
Bigger. So then, okay, if this diverges, then that means it goes to infinity. So then this one diverges because it goes to infinity as well. Does that make sense? Now, we don't know that this integral diverges, but if it does, then this integral or this series diverges. Now, what about over here? What if this one converges? then that means this goes to a finite number. Well, the series from 2 to infinity then also goes to a finite number because it cannot go to negative infinity because it's all positive, and it cannot bounce because it's all positive. So then this would converge. Well, if the series from 2 to infinity converges, then when we add in A1, you're adding a finite number to a finite number. So it's still going to converge. Maybe it's bigger than this now, but it's not bigger by enough for it to go to infinity. So the idea is that based on this picture on the right, if the improper integral, if the integral from 1 to infinity diverges, then the series diverges. Based on this picture, if the integral from 1 to infinity converges, then the series converges. So integral test says exactly that. It says that first, what I've written on the screen for integral test so far is first, you have this picture or these pictures. F of k equals ak, meaning the dots lie along this curve. F of x is continuous positive decreasing, means that it looks basically like that red graph. Does that make sense? Okay, so we have these diagrams. Then integral from 1 to infinity of f of x dx and the sum k equals 1 to infinity of ak, either both converge or both diverge. Does that make sense to everybody? Any questions on that? Okay, so the integral test is a very cumbersome test to use. There are 4 things that you have to show are true. So first, f of k has to equal ak. That's usually going to be pretty obvious, but we'll see why in a second. Second, f has to be continuous, f has to be positive, and f has to be decreasing. If all 4 of those things are true, then you get to work out an improper integral. And then whatever the answer is here is the same answer here, as far as the answer being converge or diverge. So if this converges, this one does too. If this diverges, this one does too. If this converges, though, this does not probably converge to the same number. It just converges. Does that make sense? Okay, so let's use the integral test. To show whether the series converges or diverges. Okay. Okay, somebody in chat saying they're confused. Let's see if it makes more sense once we do this definition or this example. But the idea is based on these pictures, if the integral converges, then the series does too. And if the integral diverges, then the series does too. But you have these 4 restrictive conditions before these are true, or before you can use this. So let's try it and see. And if there's specific questions, let me know. So, okay. If we're going to use the integral test, so first of all, should I use the integral test on this? Like, do you guys know how to tell whether this one converges or diverges? This was one we did early last week, probably, right? Or the week before even. What
Isn't it a P series?
Yeah, this is a P series. It converges because P is bigger than 1. Does that make sense? So we should for sure not be using the integral test, but because we're told to, let's do it just to see how this works. So what you do is you say, okay, let f of x equal 1 over x to the 4th. Okay. So in practice, typically what happens is if you're going to use the integral test, f of x is whatever this is, except x instead of k. Then, okay, we're going to say, obviously, f of k equals ak, because if you plug k in here, you get 1 over k to the fourth. Does that make sense? And we can write equals 1 over k to the fourth. Okay, that's the first thing that has to be true. Second, f is, you know what, we'll do this. We'll say f is continuous on 1 to infinity. F is positive on 1 to infinity. And now, okay, those are clear because this is only discontinuous at 0. Positive because it's a positive number over x to the fourth, which is also a positive number. And then it's decreasing. That's harder. You show that by showing that, okay, f prime of x is negative 4x to the negative 3. And prove that that's less than 0, which this is because you've got a negative number over a positive number on 1 to infinity. Okay, so the derivative is negative, and I'm doing the derivative by saying, okay, that's x to the negative, man, I'm struggling. X, negative 4x to the negative 5, negative 4 minus 1 is actually negative 5. And so either way, the proof is correct, but it's negative 4 over x to the fifth. You got a negative number over a positive number on 1 to infinity. So, okay, so these are kind of the four things you have to show before using the integral test. So if we're going to use the integral test, you say, okay, first, the function and the sequence are the same. Second, the function is continuous. Third, the function is positive. Fourth, the function is decreasing. Then, okay, the integral from 1 to infinity of that function, if this converges, then the original series converges. If this diverges, then the original series diverges. So what we do is kind of like what you guys were doing, hopefully on Monday's video. You say, okay, this is the limit as r goes to infinity of the integral from 1 to r of x to the negative fourth dx. That's then the limit as r goes to infinity of 1 over negative 3 x to the negative 3 from 1 to r. That's the limit as r goes to infinity of negative 1 over 3 x to the third from 1 to r. And now you plug in r, plug in 1, and subtract. And the limit as r goes to infinity of that is 0 minus negative a third, which is 1/3. The only thing that really matters about this number is that it is a number. And so then this integral converges. It does not matter whether it's positive. It doesn't matter whether it's bigger than 1 or smaller than 1. It's going to be positive given what we've got here. But the fact that it's a number means that the integral converges. And so then, so the series k equals 1 to infinity of 1 over k to the fourth converges by the integral test. Okay, questions on what happened there? Everybody follow what we're doing here? Okay. Now, I want to talk about two things related to this. So one thing is that in most cases, we are going to try to avoid using this because there's a lot to do. Remember that, I mean, probably what you should do here, if it doesn't tell you to use the integral test, you should say this converges because it's a P series where P is 4, which is bigger than 1. Now, last week, or maybe the week before, when we started to talk about P series, I gave that result without any proof. And the integral test is actually how you prove that result. So the fact that you ended up with a negative third power here, we ended up with x to the negative 3 here, shoved that to the bottom and made this converge. If the r ends up in the top, this diverges. The primary use for us for the integral test is to prove the P series result, the P series result that we have already done. And so for the most part, we're going to avoid using this. So I want to talk about why, well, that's the main reason we want to talk about it, but I want to show you guys a couple things on these handouts. Give me 1 second to get them pulled up. But on the integral test handout, okay, so there's a couple where you actually go through and do them. And there's 6 where you actually go through and do them, but like this is one that we just did. But the primary part is to talk about the most important part of the integral test is this, that consider the series k equals 1 to infinity of 1 over k to the p, where p is any number. The goal is to determine for what values of p the series converges and for what values of p the series diverges. We know this already, but the pages 3 and 4 of this handout take you through the proof of, okay, when do these converge and when do these diverge? And that's kind of the goal of this. If you want to practice using the integral test, there are 6 problems here. I'm not going to collect them. Most of the time we can get around using the integral test. Like for number 1, we should be using a comparison test unless we're told not to. Number 2, we should be using a comparison test. Number 3 is probably one where you actually need to use an integral test. And so you'll see in the solutions on these, let me pull those up too. Man, I lost that folder. Give me 1 second again. Sorry, guys. So if you look at the solutions on these, then, okay, this is how you do it. And here's me just, the only thing that gets harder is, okay, the derivative is a little bit harder and you're doing the integral, which is a little bit harder. It involves log or something like that. And then down here, this is probably an example where the best way to do the problem is an integral test because we're mixing up stuff. Although I think maybe we could use ratio test tomorrow on that. And then this one, same deal. It's probably best to use the integral test, but we might be able to try the ratio test, which we'll talk about tomorrow. Number 5 and 6 for sure, P series. And so anyway, the idea is we try to avoid this test. So when possible, we don't use the integral test. You have to have an idea of what's going on with it. We should understand the rationale behind it. But for our purposes, the primary use of the integral test is proving why P series work the way they do. And we've been using that result for a while, which is why this is weird. So now, other than the ratio root test, we have now covered, can you guys still see that PDF? Something weird just happened. Is that a yes?
Yeah.
Okay, cool. Just making sure. Okay, so we've now covered almost all of the series tests. We've got the K-term test for divergence, the basic series, geometric and P series, the series with all positive terms, series with some negative terms. And so we talked last week about how you basically start here and kind of go backward through this if it's alternating, or you might start here if it's already positive, or if it's already a basic series, you start here. So the majority of the series we're going to do are above this line. Well, okay, then tomorrow we're going to look at what happens when we use the ratio root test and how do we know to do that. And we'll talk about that. It's when we start to mix function types where they're not all power functions, not all exponential functions in the same problem. So if you mix them, we start to use ratio root test. And then the integral test is, in terms of most of the problems we do, is kind of an aside. It's one that you use if you absolutely have to, but for the most part, we're able to figure out ways around it, which is why we kind of de-emphasize this lecture. This lecture could have come before we started doing P-Series. I actually think it's better for you guys to do it now because now P-Series I think should be easy. But this is more, hey, we want to know why the things work the way they did. So far, it's less important for standard problems. Does that make sense? All right. Any questions, you guys, before we get out of here? Because that's all I've got for today. All right. As far as our standard problems, tomorrow's lecture is a lot more important. If you want to practice integral tests, go work that worksheet. I'm not collecting it, so you don't have to do every single problem, but it's probably a good idea to practice some. And it might be a good idea to go through that P-Series proof if you're interested in why that works. All right. That's it for today, guys. Thanks for coming.